5, 4, 3, 2, 1.
This is the first of two videos about graphing displacement and velocity. Taking measurements to determine velocity and acceleration involves measuring two things. The first is the elapsed time between 2 points along the path of motion, and the second is the change in position of the object between the same points. I'm introducing a new symbol here. That small triangle is a delta, which is from the Greek alphabet, and it means change. So for example, the change in displacement is represented by delta S. Analysis of data usually requires graphical analysis and interpretation. This is especially true when we're doing experimental work. The two basic types of graph are displacement time graphs, which is the topic of this first video, and velocity time graphs, from which the other quantities may be calculated. So let's look at displacement time graphs. The slope of an ST graph indicates velocity. Case 1 is zero velocity, where we have a flat line. In other words, the slope is zero, and this graph indicates that the object is not moving. Displacement does not change as time passes by. So velocity, which is given by delta S over delta T, will naturally just be 0 meters per second. Case 2 is constant velocity. This graph has a constant slope, so V will be constant. And in this example, the object's velocity is about 4 meters per second. The steeper the slope, the faster the object is moving, and the gentler the slope, the slower the object is moving. Case 3 is acceleration. Here you can see we have a curve and the slope is increasing. So first of all, we note that the slope is continually changing. The increasing slope indicates that the object is speeding up or accelerating. Now the instantaneous velocity at a given point in time is determined by the slope at that point. To find the gradient of a line at a point on a graph, we use gradient equals rise over run. In other words, the change in the y values divided by the change in the x values. In this case, delta S over delta T. In general, if delta T tends towards 0, in other words, the instant in time is very small, then V will give the instantaneous velocity. So if, for example, we want to calculate the velocity at the moment t equals 2.5 seconds, we construct a triangle that intersects that point on the curve, and we read off the change in the s values and divide by the change in the time values for that triangle. So reading from the graph, the upper s value is 9 and the lower s value is about 3. The upper t value is about 3.6 and the lower is about 1.9, and when we do that calculation we get approximately 3.53 meters per second.